So we are Aeronetics. My name is Vincent Mai.
I'm Ellis Munoz.
Jesus Mendes.
Jason Martinez. And our project is the deployable vertical access wind turbine. This is the overview for our presentation, what we plan to talk about.
So our project was inspired by the events of Hurricane Harvey. So after the events of Hurricane Harvey, many people were left without electricity for weeks. And after a couple of days, small devices such as radios, phones began to die off. So what we decided was to design a portable vertical access wind turbine that was safe and ready deployable, meaning it was simple to deploy. Anybody could operate it, most people, and it would produce enough power, renewable resource that it could power these small devices. Which at least the project scope for the project, it had to be portable, safe, deployable, easy to operate that most people could set it up, fairly cheap, and most importantly, generate enough clean energy to power these small devices.
So first we have the portability of it all. So far we have a gas tank, and we split it in half to make two interchangeable blades, which we plan on integrating in later on. The base shaft is also there where you can close it in, deploy it out where it needs to go. We have the legs, of course, where we can plant them in the sand and the dirt. And then we also have our generator box, I'm sorry. And we have vents in it to prevent any overheating that may be caused inside of it.
So early on in the design process, we decided to go with vertical axis wind turbine over horizontal axis wind turbine. The reason for this was that horizontal axis wind turbines are more expensive and harder to put together, which when we're trying to make it portable, which is probably the biggest part of our project, being easy to put together and take apart is really important. So after that, we had to decide between Savonius wind turbine and Darius wind turbine. The Darius wind turbine is more effective, but also, again, more costly. So we decided to go with the Savonius wind turbine. Some of the advantages is it's not affected by wind direction because it doesn't matter which way the wind's facing. At the turbine blade, the inside cup of the blade will be facing some part of the wind. So it's going to constantly keep spinning. As long as there's any amount of wind, this turbine is going to produce energy, which again is important for the portability aspect of it. No matter where we set it up, we're going to be able to produce energy. However, we are sacrificing efficiency. Ours is relatively low, keeping in mind that the maximum efficiency is around 63%. Our efficiency is going to be around 15%. On top of this, the rotational speed of the turbine is never going to exceed the wind speed. So the energy we can produce is dependent on our location. If we're in a location that has high speeds, then of course we're going to get more energy, and in locations with low speeds, this design is less than ideal. But also with that, it's going to be safer under high winds because the speed is controlled. It's not going to go fast.
So on the base design, our main thing was having it portable and compactable. So for the main base of it, we decided to have everything interchangeable to where if one part does break, we can easily replace it. One of our big designs is having the legs to where we're able to slide and extend the legs by just using a slider. And into the design, the angles for it have been calculated to be best possible based on our skills. And then for the generator box design, it is meant to be compact while still housing all of the electrical components, everything from the battery to the generator to having the flywheel assembly. And then to also prevent any overheating, we have included a vent design in the back of the generator box.
We do our electronics and electrical layout is down here, starting to the left. We have one of our two generators that we are testing in terms of use. In the middle, we have our battery here, and on the end, we have our power converter. Up top, you see our two generators. We have tested both do produce power. but we have more tested the smaller of the two generators in terms of having out in the open in wind. And during our test, we had it connected solely to our power converter, converting our DC energy to AC energy, so we can actually plug in cell phone chargers or whatnot. And we were able to get about 30 volts at a peak at about with a wind speed of between 12 and 18 miles per hour. Our battery is a smaller 12-volt DC battery, smaller just the size to fit in our gearbox. And the amp hours is a little higher than what most small-sized 12-volt batteries are, due to the fact that we wanted to have enough power to actually run our power converter, just in case there is no wind available to run the generator. The DC power converter, of course, is to convert DC to AC for use of our small electronics.
So for our design changes, the right picture is our current and final design, and the left picture is our original concept of the turbine when we first had this idea. We want to stick with the left turbine. It's the Darius wind turbine because it's more efficient, and unlike the Savonius wind turbine, it can spin faster than wind. However, that also makes it more dangerous because if winds get too high, then it can get too fast to slow down. It's also more costly. It's more difficult to design. It's more difficult to manufacture, and as a result, it's more difficult to put together. So in the end, we did decide on the Savonius wind turbine. Well, we're sacrificing efficiency. It's also a lot cheaper than the Darius wind turbine. It's a lot more simple to manufacture, simple to take apart and put together, and it is safe in conditions.
Yeah, so for our manufacturing process, we divide it into 3 stages. The bottom part of the turbine, which would be the turbine base, the middle, which is the generator box, which houses all the electrical components, and the top half, which is the fin and shaft design.
And then the manufacturing process for the base, it all started with the main plate that you see in the middle picture. That was originally cut out, was planned in AutoCAD and drawn, and then cut out on the plasma cutter to provide a accurate cutout. And then after that, the legs were manufactured, and then the connector pipes were done. And then for the generator box, we used a 1/8-inch thick aluminum sheet plate for it, and we used AutoCAD design again, and a plasma cutter in the shop to make out this outline of the box, and then we were able to form the box using tabs and plates.
For the fin and shaft design, we took a barrel, we measured it so that it's about 24 inches diameter and 24 inches horizontally and vertically. And then we measured it and we cut off the top and bottom ends. Then we cut it in half and then set up to where you see now. We're currently still working on it. We haven't welded the connectors yet to connect it to the shaft yet, but we are still in the works. This is currently our bill of material list that we have right now for our design process as of right now. We also have the legs and the electrical components as well, listening components. So far, we have used $285 just for the materials alone, and then we have the cost of the components that we also have. And then we have roughly about $30 more that we spent on bolts and any other accessories that we. This is still an ongoing number since we are not completed yet, but we are sitting at $411 that we have spent so far. So for planned testing, we plan to more or less measure the power output over time at different wind speeds at different locations, and then compare and contrast the efficiency overall at what is the best wind speed. We also want to see how long it would take to fully charge a phone or smaller device at an average wind speed in Corpus. We plan to have multiple graphs detailing different data pertaining to different wind speeds and the efficiency of the turbine, and whether or not it could work under certain conditions.
So So like most projects, we had our issues and concerns. One of the issues was the generator box assembly. So since it was built from one single sheet piece, we had to bend the tabs in and the whole piece as one. But with the machines that we have here, it was difficult to bend one without damaging the other. And so that took us a while. We were not able to 3D print yet. I think they were down, so we haven't been able to print some of the pieces that we need that go inside the generator box. One of our biggest issues was the fin design. So there is no standard design for the vertical axis wind turbines. So one of the concerns that we have is that the design that we chose will lack insufficient power to power these the small devices. It also didn't help that one of our motors was backfeeding. So one of the concerns now that we have is, do we install an actuator or do we use a smaller motor? It also didn't help that we didn't have we like the program to test the design, so we can't do most of our testing until after finished assembly. Work to be done, we still need to finish up the fins, weld, and the electrical component. So it's mainly just the top half that we need to finish, put in whichever motor we decide to put in there. Most of our testing will, again, be done after finished assembly. We'll be comparing and contrasting the data that we record and taking note of any design flaws or any potential improvements that we can realistically make before our final presentation.